Is that fine? Yes. Okay. Nice. So anybody can recap few things what we discussed, only the topic in last class. Who will recap? You can either write it down or speak it out. What did we do in the last class? Friedman equation and solve for scale factor as well as matter density, radiation density, and scale. Yeah.
After deriving the energy equation,
What else we did? Okay. So let me Gauri Shankar is joined. Okay, so I'll recap now a little bit so that you will remember. You can see the whiteboard.
yes, sir.
Okay. So who will tell me what is the first Friedman equation? This you should remember by heart now. Okay. So what is the first Friedman equation? Who will tell me? Either from note, speak it out. I'll write it down. Okay. There are two Friedman equations from where many of you have sent me the PDF of homework. It's good. Shruti to send me, Jahan send me, Avinash send me. Yes.
No.
Rest of the people, please do the homework. Otherwise, you'll not be able to understand also. Forget about exam. Okay? Slowly. Okay, so tell me the first Friedman equation.
It's A dot by A whole square equals to 8 pi G.
Okay, I'll remove 3 from this side. Yes, go ahead. 8.
8 pi G rho total by 3 minus K by A square.
Rho means rho total. Yes. All the
Yes.
matter, radiation minus K
K
by
by
A square. Very nice. And the second Friedman equation?
A double dot by A equals to minus 4 pi G by 3.
Into minus 4 pi G by 3.
Times rho total plus 3 times P total.
This is good. And from these two equations, you can get the continuity equation, which is not an independent equation, which is what? D rho by dt. Some of you have done it. Plus 3 H rho plus P equals to 0. Yes, right? Yeah, some of you have derived. Yes? If you have not derived, please do it. This will be the pillar of. Okay. So now this is called continuity equation. Either this, you can take any of this one, this is equation 2, this is equation 3. Any of the two out of these three are independent. So now let us take the continuity equation, this one. This continuity equation. And from here, if I give you P equals to W rho, means I'm not specifying what is W. W is 1, minus 1 for cosmological constants, 0 for matter, 1/3 for radiation. Then can you solve from this equation how you put it here, A dot by A and solve for rho as a function of A. So dt can be cancelled out. You will find out. So can you do it now? What is by put this p equals to w? I want a general solution. We have done it for matter, we have done it for radiation, but from continuity equation, please integrate out and do it right now. Okay, is it clear now? Yes. Please do it now and find out. Tell me the answer when you get it. Once you're done, tell me. As a function of w, I want. Okay. You continue solving. I am drawing some picture. So somebody got the answer. Let me see. So Shruti is saying rho is equal to e to the power. E to the power नहीं होगा. Some e to the power
minus 3 times
हाँ? Tell me louder.
A to the power minus 3 into w plus 1 omega plus.
This is the answer. Some constant time. Yes. There will be an integration constant. Okay.
Yes, sir.
Okay. Very good. So those who did not get it, it is very easy. Or you talk to Jahan later because I am just doing it from last class only to recap a little bit. So now you can see if you put w equals to 0, what will be the rho? How it is going? A to the power minus. What is w equals to 0? Matter for matter or dark matter, what is the value of w? W is basically pressure, no? P is equal to w times rho. So for matter and dark matter, what is the value of w? Tell me. Huh?
0.
So rho goes as rho naught into a to the power minus 3. Yes? That is matching. We have done it before, no? 1 by a cube. Yes?
Yes, sir.
And for radiation, W is how much?
1/3.
1/3. So rho will go as
8 to the power minus
8 to the
4.
minus 4.
and W equals to how much for dark energy? Cosmological constant.
Minus 1.
So the rho will be
Constant, right? Rho 0.
So now you see from here, I am plotting the same rho I as a function of log of AI. Log AI means log A. So A means scale factor. So scale factor 1 means at present time now. So this will be the 0 in the plot and this side will be the negative. So minus minus 40, minus 60 means 10 to the power minus 60. The universe was very small. Okay, so this is a new way of writing, as I told you before. Either you make this number 1 and previous number very small, a scale factor, or make scale factor in the beginning 1, then today you will be having number like 10 to the power 60, 10 to the power, because universe has become very big. So that will be very annoying to write 10 to the power, because we see things today only. So we normalize it to today now as a equals to normalization 1 scale factor. That's why in the early time it is small. So now which line here is for what? Can you tell me? This line is for matter or radiation? Top line?
That's radiation.
Because it's going faster, yes?
Yes, sir.
So this part, you see radiation was dominating in the beginning. That's why early is called radiation dominated era, RDE. We have talked about it before, yes? And then you can see the matter takes over as we progress in time, and this era is what era? From here till the dark energy takes it over. The dark energy, this is lambda, because this is a constant, cosmological constant. You see, it's a constant. So what will be this part called? Who can tell me? What?
Matter dominated.
Very nice. So when did galaxy form in the universe? Radiation dominated era or matter dominated era?
The matter dominated era, sir.
Very nice. And then dark energy take over. This happens around when a universe is 8 billion year old, or 9. Means Earth just has formed, Sun has formed. Then from now onwards till now, this is what dominated era? Till now?
Dark
energy.
Dark energy dominated era. Dark energy, DED, dark energy dominated era. So universe goes through these 3 phases. Okay. So now, today we'll be going through a little bit very important concept. So today's lecture is less on mathematics. What I will be doing till now, it is recap. But it will be very important on concepts. Okay. So till now it is all clear, and also we have solved in the last class how scale factor, because once you know how it goes as function of a, you can put it back into the Friedman equation again, putting k equals to 0. We know k equals to 0. Then we find at as a function of time in different dominated era. So radiation dominated era, what is the solution for radiation dominated era? How scale factor expand as a function of time? Who can tell me? We solved last.
1.5.
E to the power half. You remember? Yes, all of you?
Yes, sir. Yes, sir.
Then for those who know already saying, don't answer again. For matter dominated era, how? What is the power? Yes, very nice. And for dark energy, who can tell?
Exponential.
Exponential lambda t. Very nice. This is a constant lambda t. This is dark energy. So you can see universe. We starting from GR, starting from the metric definition of we're starting from special relativity. Then we added the co-moving coordinate. We said that special relativity metric will not work. We need to multiply it by scale factor, and then minus c squared dt squared plus s squared into this term. And then we use the Einstein's GR equation. Those we have not derived, but we have told you that once you know the metric, left side can be calculated by Mathematica or any software. It's a curvature calculation. That curvature calculation gives you this term, a dot by s squared, and the right side is rho and p. So you all did, three of you did the homework. You have sent me that if universe is a homogeneous and isotropic medium, which is the assumption of cosmology, then this is P and rho enters into the metric, it is rho minus P minus P minus P, T mu nu. We all know it, yes? And that's why minus P minus P minus P. So that's why you see that rho plus P, all these terms are entering. Because G mu nu is the A dot and A square, the two equations, and this is the circuit. So this is still how much we have done, and from there we have seen that universe today is dark matter energy dominated. So today the universe is like this, 70%. How much? 70% is what? You tell me.
Dark energy.
Dark energy is lambda, or dark energy. We don't know what it is. And this one is dark matter, which we'll discuss later, dm, and this is the all 4%. So this is 26%. And this is the 4% is our visible universe, galaxy, all the things you see or will be seeing in future telescope. So now you can see that 96% of the universe is unknown, and we only know this much. So we are struggling to know what is this lambda and what is this dark matter. Yesterday, last class, we have understood that the value of lambda is philosophically not only for our existence to be here, this 70%, the value of lambda, what we find experimentally is very important. It's a very tiny number, as you remember. What is the value? Can somebody tell, theoretically calculated and experimentally? What is the ratio? How much lambda experiment we found?
10 to the power minus 120.
10 to the power minus 120 times lambda theory. This is the biggest mismatch ever we know in theory, history of physics. But this number is very important for us to be here. As we know, if we, instead of 10 to the power minus 120, if we use 10 to the power minus 118, say, that means we erase 2 zeros after decimal, that means this will go high up, because we are increasing it by 2 orders of magnitude. And it will cross the matter a little bit early. But most of the galaxy has been found towards the end of the matter-dominated era. It was the preparation in the beginning. So if you increase the dark energy little bit, erase out of 120 zeros, if you erase 1 or 2 zeros fine-tuning, which anyway, these 120 zeros are by hand. We don't know why it is. Nobody has even come up with any calculation. So then if you erase 1, 2 zeros, suppose like, okay, doesn't matter. Anyway, it's a very small number. I will erase it. Then what will happen? You will see that the galaxy cannot form, because in dark energy domination will start early, because it will start here, and once exponential expansion happens, then galaxy cannot form, because it's a very rapid expansion. Space is moving away, and you cannot produce galaxy. Is it clear now? Till now?
Yes, sir.
Yes, sir.
Now, today we'll be going through some important discussion. By the way, first thing, this also you should know before the important discussion, Newton versus Einstein. Newton said, suppose you have a mass of some sphere, and if you have another mass, m, both one is m2, so both are m, sorry, forget about it, m naught, to make life simple. But this is made up of, say, very heavy objects, say, for example, iron, and this is iron. But their mass is m naught, m naught. Now, let me take another situation where the mass is the same, m naught, but it is made up of some very relativistic gas. And this one is also m naught, but made up of very highly relativistic gas. That means here the pressure is not zero. Pressure is not zero. As we remember, for relativistic species or gas, pressure is not zero, but for matter, like say heavy matter, iron, all these things matters, pressure is zero. Which means what? Suppose if you puncture a balloon of iron, make it a puncture here, the iron will not come out because it's a solid ball. But if you here puncture, gases will leak and come out. That means gas has a pressure, but iron does not. Is it clear?
Yes.
Yes, sir.
Yes? So now you tell me what is the force of attraction according to Newton between these two balls. You can assume the center of mass is at the m naught. So what will be the force? Tell me.
GMM by
G
M A by
m
M
square
by
by r square.
R square.
But Newton said whether it has pressure or not, the force only depends on the mass. So according to Newton, the second time force will be also, tell me, G m naught square by r square. Because as long as you know the mass of the object, center mass, point of mass, you know what is the force of gravity. Yes or no?
Yes, sir.
Yes, sir.
This is wrong from Einstein. Einstein says GR, because it has a pressure and a GR pressure enters GR, it will modify the curvature of space in a different way than the first case. Means here the curvature will be a little bit deeper. Here the curvature will be a little bit flat. And we know that curvature is nothing but gravity because the attraction is just because of the curvature. We show you video one day when you introduce. So if curvature is more, the attraction will be more. So this is completely different than Einstein's versus Newton. Einstein case, the gravity also depends on state of matter. That means whether pressure is not zero, that means in other way W. And that is the reason basically different W is giving different expansion of the universe. W equals to 0, different expansion means different scale factor. And different scale factor means different metric. And different metrics means different geometry. And different geometry means different gravity. Clear? Yes? Shall I repeat it or clear?
Yes.
So scale factor different means metric is different because you know the scale factor goes into the metric. D square is equal to minus c square dt square plus a square t. Sorry. 1 minus k r square. Dot. So if AT value varies differently, that means the geometry, the distance varies differently. And geometry varies differently means the curvature, the curved space varies differently. How much is the curvature? That's the reason. So know that in FRW metric, Friedman, Robertson, Walker metric of cosmology, AT basically determines the curvature. And that's why in the left-hand side of Einstein's equation, G mu nu, it is the curvature term, no? This A dot by A terms enters, A double dot terms enter in the equation. It's just the value of A and its functional form changes the G mu nu. And basically, when we solve for AT, we are actually solving for curvature of the universe, space-time curvature. So this is just, I just wanted to know that difference between Newton and Einstein is very interesting. Newton will never say if you change pressure, the space will have different curvature, but it is true. In fact, a gas of sun, depending on that, or a solid ball of iron, same mass will have different attraction because pressure is different. Did you know this? Yes or no?
No, sir.
Yes, sir.
No. So now you know that pressure can change gravity. Ravi, did you know this? That pressure will have different attraction, gravity, GMM by r square? Didn't know, no?
Yes, sir.
Very nice. So this is the Einstein's genius, okay? So now we are going to enter very important important calculation today. Are you all ready? The concept of horizon and some problems with this Big Bang cosmology and why we need inflation in the beginning. That means shuru mein bhi, in the beginning we also need there is a dark energy domination in the beginning that we will prove today. So till now we have been doing it hot plasma radiation, then matter dominated era, then dark energy. But today we will prove that in the beginning also we can have a dark energy. So let us turn on the video, break, okay, and then we'll all start this, okay. Avinash, other people, video, okay, very nice. Gauri, you are enjoying? Yes, yes, very nice. Avinash, you are enjoying? So Avinash, do you play guitar? I see that you have a guitar in your picture. I play guitar. So I have electric guitar. Maybe last class I'll play for you. Okay, very nice. I do a lot of stuff. Okay. Anything else? You are at your hometown. Corona safe.
Yes, sir.
Nowadays, positive is a negative term. You know, if you say I am positive, that means it's a very negative term, isn't it? If you say I am negative, that means you are positive. Yes. Okay. So Ravi, in IIA campus, the students are all better now.
2 more cases has arrived. So
Oh, has arrived.
uh,
Okay. So you are all still quarantined, all of you.
yes. So like, but food we started to take down. Like
Okay.
so we have allotted the slots, like 10-minute slots. We can go down and take.
So for Pondicherry University, what is the plan when they are asking you to come? Any idea?
We won't call back.
Huh?
They're not calling back. We have to learn.
And so you have not seen Pondicherry University yet?
Yes, sir. Yes.
Oh, first semester you were there.
Yes.
First semester means last year.
Yeah.
2019.
So first semester last year means last year, February, January, like that. Yes?
Yes. Till 2020. April.
Okay. So yeah, that time I was there because I was physically there, and then in the middle of the thing, because it is a 2 weeks course. When we teach physically, you know that, no? We go, each professor goes for 2 weeks. So I was staying in that guest house near that radio station, no? That is the guest house, no? Radio station, and in front of the gate. So I came on Saturday, Sunday back to Bangalore. I drove my car just to see my family, and I kept my luggage, clothes. They're still there 1.5 years because I never went back, because I came here and it's all lockdown. So a whole city lockdown. So hopefully one day I called the guest house. They said like, sir, your luggage is still here. I said like, I have not gone yet. So 1.5 years passed by, almost 1 year 3 months. Last March it started, no, the lockdown. Okay, very nice. Okay, good. So now switch off the video and you will get back into the physics. Okay, very nice. Yes. Okay, so now I'll share some part. I'll go little fast, and some part I will talk to you in the thing. But if you don't understand, I'll expand, because now I'll share a note. You can see it.
Yes.
Yes, sir.
Because I don't see you guys, so you have to say yes or no. Yes?
Yes, sir.
Okay. So now we'll talk about horizon, the real definition of horizon. Till now we have a vague definition that a distance after which we actually see that, because the universe space is expanding, because we know that as we go farther and farther, the space will expand faster and faster, and at some point you will get a velocity which is velocity of light. And then if space expands faster than the velocity of light, you cannot see anything from there. Okay, so that's how we naively thought horizon is, but now it is a little bit different. So now the way it is happening, okay, I'll just draw a little bit, then it will be easier for you. Suppose a light ray, a horizon is a sphere, you are here, all direction, I am not drawing, okay, drawing. Suppose light ray emitted long back in the beginning of universe, it is coming to you. Now, if we know that the age of the universe is t naught, roughly we will think that the distance travel is ct naught. But this is not the case. But suppose say light has traveled up to this point and it is still traveling midway, but this distance is stretching up because of the expansion. If it will be all fixed, space does not move, then it will be ct naught distance. But as space is expanding, so we will see actually our horizon dh. So our horizon dh is actually greater than ct naught because the space is expanding. The photon is coming, but behind the space, suppose this is the last point where a star was there. It is not a star, say some example, hydrogen gas, but it has moved away from this. So space is also helping to separate out the distance. So that's why horizon size is greater than ct naught. Is it clear concept-wise?
Yes, sir.
Yes.
Everybody clear? Okay. So now let us go back to actually see. So now let us see a photon particle. So as we are talking about light, for light geodesic ds square is equal to 0. You remember? Yes?
Yes, sir.
Yes, sir.
Now put ds is equal to 0, you get this equation. This is not A, this is C by the way. Okay, the C. This is the from FRW metric. Put k equals to 0 and only take the radial direction because we are only talking about a spherical symmetric situation. Light is not curving, it's coming straight. So now say it is the beginning of the universe, today is the time t naught. And we want to know what is the distance, 0 to r, we want to see. Now once we get this r is the coordinate distance. You remember this is the marked on the coordinate between 2 points, but the actual distance is this r, what we will find from this integral, co-moving distance, times the scale factor today, a t naught. So you see the co-moving distance is c dt by a, so this integral 0 to t naught, age of the universe, from which the light is traveling, times I want physical distance, so I multiply it with the scale factor. Is it clear?
Yes,
Yes,
sir.
sir.
Yes.
Now take your pen and paper and find out if radiation, say if universe is matter dominated, for example, only, then you know what is AT goes on. So what will be the horizon size? Calculate and tell me. Once you get the answer, tell me.
So can you repeat the question?
See, I now know the analytical formula of horizon size. Now I want to see that what is the horizon size if universe is matter dominated only. AT. So you know how AT is a function of time in matter dominated universe. Put it back here and solve for this as a function of T naught. I want to calculate dH T naught. Is it clear now?
Yes, sir.
Tell me how. You guys calculate. I'll just take a urgent call, 2 minutes. You can write down your answer in the chat box. Okay. Hello. Yes. Let me see the answer. The answer is the first one, 3 CT naught. It will not become on t to the power 1/3 or anything. Can you hear me? So this is the answer. DH. I think because Avinash, Jahang, you missed a factor of 8 T naught, which will be the C, which will be t to the power t naught to the power 2/3.
Yes, sir. Yes, yes, yes.
And then if you multiply this, it will be
T power 1. Yes, correct.
Gauri, tumhara bhi, it is t naught to the power 1/3, but you have not multiplied it by a t naught. Is it clear
Yes,
for everybody?
Yes, sir.
Yes? So it will become 3 CT naught. You should exactly find out the factor of 3 in front, because it's very important. It's an integral. Now if you do it for radiation dominated universe, radiation, then it to the power half, then you will find horizon size is 2 C naught, 2 CT. So you can see that we are seeing, if universe was not expanding, we will only see CT distance. Light will travel for time t by times velocity c, but we are seeing much higher. So our horizon size is actually not 14 billion years light year, it is actually 3 times 14 billion light year. Is it clear? 3 or 2 in between, because some part has been matter, some part has been radiation. Clear? But matter is the most, because see, 0.3 million years tak was radiation, but from there onwards is mainly matter. It doesn't mean that light is moving faster than CT, moving velocity is 3c. No, it means the space behind is expanding. Is it clear?
Yes,
Yes, sir.
So, yeah. Now, I'll get into another thing which is very important. This is another quantity, another useful quantity is the called Hubble radius. So Hubble radius is nothing but CH inverse. Nothing but CH inverse. So H is equal to 1/t. Just hold on, one just person came onto the gate. You just look into the notes till now. Okay, so now this H is a local quantity because H is a dot by a. It depends on the expansion of the universe at a given time. It is not an integral. So it does not involve any integrating out. But whereas horizon is an integral. So H tells you CH inverse. So what is H? H is let me do this. These are very important concepts now in cosmology. So H enters from Friedman equation, you know. So H inverse, CH inverse is called Hubble radius. What does it mean? So what is H? Tell me. H is a dot by
A.
A.
A. So now A, say for example, if you are in radiation dominated era, then what will be A dot by A? Tell me. T to the power half is the thing, so half, T to the power minus half, and that. Yes, for radiation dominated universe, I am just using the A goes as T to the power half. For matter dominated universe, what is A dot by A? Tell me. A goes as T to the power 2/3, so it will be 2 by 3 T. Is it clear?
Yes, sir.
So you see, both cases is goes as 1 by T. So you can see actually it's a time, but CH inverse is the Hubble. So H inverse, that is H. So CH inverse is C times 2T in radiation dominated universe. And for matter dominated universe, it will be C times 3 by 2 in matter dominated universe. You can see that it is for radiation dominated universe, CH inverse is same as horizon size. So more or less it is close to horizon. But for matter dominated universe, it is not 3 CT, it is 3 by 2 CT. So little bit different, but Hubble radius, H inverse, what we call as Hubble radius, is a local length scale. That means you will see later that within this any distance which is below this local length scale, within this horizon, within this Hubble radius, they become dynamical, means they get into the Newton's law attraction, they start forming galaxy. But if some distance are beyond Hubble radius, then they don't do anything. Basically later we'll know that this Hubble radius in cosmology acts as a boundary. So this is the horizon, but horizon and Hubble radius are different. We just saw. It can be same but similar. But for example, say this is Hubble radius. So anything between inside Hubble radius will be under physical law, but above Hubble radius, beyond, they will be frozen. Frozen means you will see later if we get time, equations will come such a way that there will be no dynamics. So density galaxy will not form, they will be like static. The moment they enter the Hubble radius, the galaxy will form. So why it is like that? More or less we know that inside the horizon, because now Hubble radius is same almost as horizon. Outside the horizon there is no causality, no causal universe. So that means there is no physical law works there. But inside the horizon, only we know that under the physics, because outside the horizon, the things are moving much faster than velocity of light, and the physical laws, universe is very different. Okay, so that's why all the normal universe we see is within the horizon or Hubble radius. They are more or less same, but actual number is Hubble radius, which matters for cosmology. So now, let us go a little bit more deeper. The concept will be a little tougher, but it will be easy, not so hard. So now you see, the Hubble radius is done. Now I will do another thing. Another concept is called lambda physical. This is very easy to understand. That is basically, suppose there is 2 points in the universe which is far apart. Their distance is lambda co-moving, but actual physical distance is AT times lambda co-moving. Is that clear? Because I have to multiply by scale factor, yes?
Yes.
So now, this is a very important thing. any physical distance, suppose you take a ruler of one light year, 1 billion light year. Now, if you wait for another epoch when scale factor becomes double, what will be the size of the ruler? Is the question clear? Or shall I say it again?
Yes, twice of.
I say that this is my universe. Now I take a scale ruler, imagine a hypothetical scale through which I measure the distance, and this distance is 1 billion light year. 1 billion. Okay. Now, if I wait for another some time, when now the scale factor is, say, it is a equals to, for example, I'm just giving a number, say X scale factor is some value AI, and now I wait for few more cosmological epoch, and I find new scale factor as A final, and AF is 2 times AI. That means universe has expanded 2 times in all directions. What will be the length of this scale? Actual physical length.
That will be same.
Huh?
It should be the same, right?
Why?
It should remain same.
Why? Because we discussed that any wavelength also changes, lambda. Everything is stretched. So why the ruler will not be stretched? If space stretches, so any physical distance, lambda, why I know what you are saying. If I take this x2 and this is x1, then x2 minus x1, suppose it is a one dimension, that is the co-moving distance. Lambda co-moving means it is moving with the coordinate. That does not change. But physical distance is AT times lambda co-moving. So which will be 2 because it has become 2 times 1 billion light year. Is it clear?
Yes, sir.
Yes, sir.
So don't think that only space expands. If you are like lying down like that, you will also expand. Okay? In stretch. Everything in space will be stretched. But of course, large distance will be able to find it. This large distance are subject to expansion of the space. Small distance, say the solar system, the distance between Earth and Moon, they will not change because the gravity is so powerful here. It has already separated out from the expansion of the space. So they will keep the balance thing. The distance between 2 atoms in a molecule will be same. But large distance will be expand, like the distance between 2 galaxies. Say I have a galaxy here, I have a galaxy here. The co-moving distance is 1 billion light year, but the physical distance will change because the space inside the galaxy is expanding. That is what Hubble expansion is. Is it clear?
Sir, can you explain why it doesn't affect the small scale?
See, what is happening, suppose space is expanding. A very important question you ask. Small distance means they have a more gravitational attraction. Yes?
Yes, sir.
And they are now out of the flow of the cosmos because now their attraction is so high that even if space wants to stretch them, they will hold back there. So it is almost like you have a strong spring and you are holding 2-point particle, P1 and P2 by a spring. Now space wants to expand, but the spring constant is so high that is keep the distance fixed. Got the point?
Yes, sir.
But suppose you are in a very large distance, then gravity is so weak. Here is a galaxy, here is a galaxy. There is no attraction between them that much. So then the flow of space, AT, is stretching. That's why even if you have a lambda of photon, The photon lambda does not have experience, they have no mass. They don't have mass, so that's why lambda will be 2 lambda, because space has become expanded 2 times. Is it clear?
Yes, sir.
That's why all wavelength will become proportional to scale factor. So now we are entering a very nice idea of cosmology, which is the heart of cosmology, which many people don't understand. Now, let us write it down. dH, horizon size, means the physical size of the universe, causal universe. Beyond that, we don't interact. It's 3 CT in matter dominant, 2 CT, C is 1, I am writing down. Now, if you write T in terms of scale factor, how much it will be for matter dominated data?
T to the power 2 by 3.
No, A goes as T to the power 2 by 3, so T goes as A to the power.
3 by 2, yeah, right.
3 by 2.
So I'm now I'm now finding horizon as a size of as a function of scale factor by substituting T as a function of A. Is it clear?
Yes, sir.
For radiation dominated era is 2T, and you know that A goes as T to the power half, so T will be going as A squared. Is it clear? So now, oops, sorry. A very important concept is coming up now. Now, what I find, the horizon size, dH, goes as A to the power 3 by 2 in radiation dominated era, or goes as A square in matter dominated era. So now if I plot my horizon size, dH, as a function of log of dH by log of A, then it will be and for, can you calculate for dark energy dominated era, cosmological constant or dark energy dominated era, how will horizon will go? Horizon is more or less like CT. Sorry, horizon is more or less like H inverse. And for cosmological constant, we know that from Friedman equation, A square is equal to 8 pi G by 3 times rho, and rho is a constant. So H is constant. So H inverse is also constant. So that means the horizon size actually does not change. It's a constant if it is dark energy dominated era. So now I tell you, I have not proved you that in the beginning universe was dark energy dominated. So horizon size is constant. Then radiation dominated horizon size will go as A to the power 3 by 2, and then sorry.
So it should be opposite, right?
Huh?
In radiation dominated, it should be A square. Right?
Okay, sorry. It's the other way around. Is it true for radiation A square? Because T to the power half, no? Yes. So, so you tell me how the horizon size will go in radiation dominated, how the slope will be in log dH versus log A. So this is a medium one slope. That means it goes as A, but it is going as in radiation goes as A square. So what will be the slope? Little bit higher or lower?
Higher 2.
This. And then when universe enter matter dominated era, it will be little bit less slope. It would have gone like this, but it has gone from a square to a to the power 3 by 2. So the plot is like constant a square, then a to the power 3 by 2. This is the size of the horizon. So anything which is inside is within our physical universe. Oh, sorry. Within our physical universe, which is below, because the higher dh means this is dh is this line. Beyond this is outside horizon, inside is this. Now you tell me any distance. Suppose I have different wavelengths. I am drawing it here. This concept is little bit thing, but I am drawing different log of lambda I. Different wavelengths. So wavelength of 1 megaparsec, 2 megaparsec, 3 megaparsec, 4 megaparsec. But I just said that wavelength will just go as A will expand as A. Because lambda physical is A times lambda co-moving. So wavelength physical distance lambda will be stressed as A proportional, and log A may, how will be the slope? It will be steeper than this or lower than this? Who can tell? Physical distance, the slope. This, if I plot it in the same plot, log different length scale. Suppose I start with a ruler here, 1 megaparsec, and as the scale factor expand, it become 2 megaparsec, 4 megaparsec, 6 megaparsec, 8 megaparsec. And if we start with a 10 light year, 10 megaparsec scale, it will become 20 megaparsec, 40 megaparsec. So that's why the slope are the same, because they are all stretching as a scale factor. So here it is higher than that. See, it is a square and this is a to the power 3 by 2. So my slope will be actually, will be like this, less steeper. So now I am drawing, I'm going back to the exact thing. After I show you this, it will be clear. See, this is the physical wavelength. That means what? It higher means what? Say I can think of the like a, say this becoming higher, physical becoming higher means I'm looking galaxies which are further apart. So here means I am looking at a galaxy which is say billions of light years apart. Here I am looking, their physical distance is less, so maybe million of light year apart. Here is maybe 0.1 light year apart. So different distance or different length scale. Now you can see as universe expand, this one is the horizon I have just derived, how they go as a function of scale factor. Whereas different higher length scale come inside our horizon. Is it clear? They are crossing. They are not parallel to the horizon size. Is it clear from the picture? Yes?
Yes, sir.
That means bigger length scale will come inside our universe. Which means what? Which means in radiation dominated or in matter dominated universe, more and more stars come inside our universe. So now I will explain you what is happening is very interesting. Physical.
So smaller scales coming faster in horizon and larger scales slow.
Larger
Like
scales are coming inside. So this is what happening. This is your horizon, and horizon is expanding faster than the distance between points because of the expansion of the space. So suppose I have distance between two stars which are yet to be inside my horizon. This is star 1, S2, and this is star 1, S1. Their distance is very far, say lambda S1, S2. But as universe expand, this goes as A. But whereas the horizon size inside we are here, that diameter or the horizon inside, as much radius or diameter, whatever, goes as a to the power 3 by 2 or a square. So this one will expand faster than A. So after some time, if I wait, I will see that S1 and S2, this distance has come inside my universe. Is it clear?
Yes, sir.
These concepts are very tricky. You have to read it again and again, but intuitively, many of you are getting it little bit, that my horizon is expanding faster, goes as a to the power 3 by 2 in matter dominated S square in radiation, whereas my distance between object is going as A. So which one wins?
Horizon.
Horizon wins. Horizon is becoming bigger, so things are coming inside. This is the whole game. But now, can you tell me what happens in dark energy dominated universe? How is the horizon go as a function of A? How is the DH as a function of A in cosmology in dark energy, lambda dominated universe? I just told you. Can you tell me?
It's a constant. Constant, right?
Constant. Very nice. So then what will happen? Suppose I have my distance S1 and S2. See, S1, S2 will always goes as A. There is no problem. But horizon size now, DH in lambda dominated universe is a constant. So which one will win now?
Distances will be now.
Scale factor. That means now in dark energy dominated era, if you wait a little bit, suppose S1 and S2 was inside, and if you wait a little bit, you'll see they go outside of your universe. That makes sense because universe is expanding so fast that the distance between 2 points are going farther away. And that's why if you wait for 5 billion years, you will see no galaxy inside our universe. Only you are alone, Milky Way. All S3, S4 billions of galaxy cluster will go outside the horizon because A will win over constant. Is it clear? Little bit?
Yes, sir.
Yes, sir.
You have to study it, note, you have to think about it. Then only, these are very tough concepts of modern cosmology and it's not so straightforward. So now, if I had a line here, again, can you see my cursor?
Yes, sir. Yes, sir.
I have to draw a parallel line here for dark energy dominated universe because it's constant. Then you will see, if you stretch this lambda 1, lambda 2, lambda 3, lambda 4, they will again go out of the horizon because there will be a constant line. For example, take the upper line of the shadow, brown, gray shadow. And if you extend lambda 4, lambda 3, lambda 2, lambda 1, then they will again go out of the horizon. Now,
Here, sir, hello, sir.
yes, go ahead.
So here, lambda 4 is the largest now.
Yes, so the bigger scale will leave earlier. So which enters later, which comes inside horizon later, that will leave earlier.
Okay.
So if in matter dominated universe or in radiation dominated universe, which scales enter in our horizon fast earlier, small scale or bigger scale? Ravi, you don't say. Okay, other people. Can you tell me? Which scale? Which upper one is higher or lower one is higher?
Upper one is higher.
So that means lower scales are entering your horizon fast, isn't
Yes.
it?
Yes.
And then the later scale. So that means small distances will come inside your horizon, stars, but larger distance are coming today, late. But then larger distance will go away. That means stars which are farther away, which we have not seen them yet, they will come in later, two stars between their distance between huge, and they will leave immediately. So we are living in a very special time, amazing time in cosmos, where dark energy just started dominating, so it has not thrown all the galaxy out of the universe. So we can see. And that's why we saw the video last time. You know that, no? That if you wait for 5-6 billion years, then you will see all the galaxies, S1, S2, S5, all will go away, and you will see an empty universe, only Milky Way. And if you wait even longer, then Milky Way will also start stretching, and will lose the galaxy and of the Milky Way also. Not the galaxy, the stars. Is it clear?
Yes.
Yes, sir.
So this picture you should memorize very nicely. Think about it. This is the my horizon size. I have just derived a square a to the power 3. And this is the right side is the time or scale factor, whatever is expanding. So this is my boundary. Above it is not within causal horizon. We cannot see them. Below it is, we can see them, we can measure them. So you can see things enter universe and they will leave universe in dark energy. And you cannot see them anymore. But we are now here, just dark energy has started here. So all the scales are inside, most of them. And that's why we can see galaxy clusters, we can see nebulas, we can see, the intergalactic space, and we can see the hydrogen, we can see many things which universe is revealing. But if human would come 4 billion years later, they will leave us and you will see nothing. So somehow the universe wanted human to be here in a right time, where universe can reveals its maximum beauty and secret. And that's why this time is the most important one for doing cosmology, where life has sprung on the earth. Okay? Clear?
Yes, sir.
So now I'll tell one more thing and then we are done. This will elaborate in a much better way next time. So now, this is my CMB sphere, you know that. We are here. This is a disk where photon has been released. We have discussed about it. And coming to us, CMB, cosmic microwave background photon. Yes? Everybody remember?
Yes.
Yes, sir.
Now, what time CMB was released? How old was universe?
0.3 million.
0.3 million years.
Roughly, what was the horizon size that time? CH inverse, which is CT almost. We have done it. So 0.3 million light year. Yes, roughly.
Yes, sir.
So that means when CMB was released, that time the horizon size was very small. Today our horizon size has become very big, 14 billion light year times 3 actually, or 2 we have discussed. So it's pretty big, the whole thing is our horizon. But that time, the horizon size was very small. So if you take a photon here, its own horizon size was this much. That is basically the radius was 0.3 million light year. Clear? That time the horizon size was smaller, isn't it? Because the age of the universe was very less that time, isn't it? Means what is the maximum distance light could travel? More or less this. You might get a factor of 2 here, I just said, because this 2 is coming from the expansion in the radiation dominated universe. But more or less 0.6 million light year. Clear?
Yes, sir.
So these points, this sphere, this sphere, this sphere, now the distance between, they were at that time beyond their causal horizon. That means this can never interact with this bubble can never interact with this bubble, because all they can interact is within themselves, because that is the maximum distance light can travel till that time of the universe. Is it clear? So an atoms here or a photon here will never know what happening in the photon here or photon here or photon here, because they didn't get enough time because their maximum boundary is this much from the starting of the Big Bang till now. Till that time they were epoch. I am talking about that time, not today. When photon was getting released, what was the size of the horizon? Is it clear?
Yes, sir.
Now, that means this photon gamma, this photon gamma, this photon gamma, this photon, and with a small boundary. So there are, say, I am just giving you, say say there are 10 to the power 5 photon here, there are 10 to the power 5 photon here, on an average, the uniform density. So these bunches of 10 to the power 5 photons in each, they will not have causal contact. These have never been in causal contact because they were outside the horizon. So there is no way light can travel. But amazingly, when we see this one is also 2.7 Kelvin exactly. This one is 2.7 Kelvin. This one is 2.7 Kelvin. This one is 2. All the patches are 2. In fact, we know that in CMB sky, if you draw a line here, this degree of horizon, that time is 1 degree actually. 1 degree. You know, you can calculate. So 1 degree patches are within horizon. But this photon, this photon, this photon, this photon, this photon, this photon, all are at 2.7 Kelvin. Then the physicist question, how come this photon here have contacted that you should be better in 2.7 Kelvin? That means they are in thermal contact. But there is no way it can have a thermal interaction because they have never seen each other. To travel this much distance, it takes way more than the age of the universe that time. So now the question comes, how this photon and this photon know that they all have to be 2.7 Kelvin. This is called horizon problem of cosmology. That why all of them know in the same temperature, but they are not inside their horizon, so they didn't get time to interact. Now the question is, the solution to this comes. Maybe there was something in the beginning of universe where all these bubbles were inside a very small distance and then they go faster, much faster than the speed of light. Expand, speed of light, they expand like a balloon, very rapid exponential expansion, again e to the power lambda prime t, not the dark energy, the surume in the beginning of universe. So then what happens, they were once at a time in a causal contact, but then they are blown up into infinity by a super expansion, and then that expansion rate has to be much faster than the expansion velocity of light. Then only you can bring them so further apart. So when I tell this bubble, this bubble, this bubble, this bubble are not in thermal contact, I assume more or less the space is expanding, the horizon is expanding in 2 CT. The physical length scale. But if there is an exponential expansion, lambda physical, in the beginning of the universe, then it will be AT times lambda co-moving. Small distance, so small stretch wavelength lambda co-moving, they are longer. Now AT, if it is a very super fast lambda t in the beginning, say lambda, I am calling it lambda prime. Lambda prime is much higher than our present lambda because it is in the beginning. So there is a tremendous expansion happens in the beginning. Then what will happen? Lambda physical will blow up like an exponential times lambda co-moving. So that means these photons which were in a small distance, that will blow up to infinity because of the expansion, and that can only make this problem solved. So that means Shurume in the beginning there has to be a super fast exponential expansion so that they all go infinity away. So they should not be in causal contact, but they have been causal contact because space has expanded much faster than the speed of light, because you can see the AT is e to the power lambda prime t, while the speed of light is ct. So this goes faster. So that means you need an beginning make dark energy, otherwise you can never explain why 2.7 in every direction. I just told you, now go through Google search or pole vent tunnel horizon problem. Think about it. It is not so easy to understand. Think about it. Then next class I'll again discuss. Is that okay? Yes?
Yes.
Yes, sir.
Do you have any naive question about this horizon problem? Stupid question you can ask.
They're not like exactly close to horizon problem. So if we think like we existed much before time, like early universe, could we have seen like the edge of the universe like much closer?
And that's what we are doing, no? This is only edge of the universe only, this CMB. It is 0.3 million. We have seen the fossilization, which is 0.3 million light year, million year, which is very early universe compared to 14 billion years. But if you want to go even beyond this CMB, then you need this, what I told one day, that gravity wave search, which comes at the time t equals to 0, singularity. Then only you can see the edge of the universe. Okay? But because before this CMB, there was no light. As I told you, light was doing random walk with the photon, with the plasma state. You remember? So there was light, but light was not able to travel freely. So if there was no traveling freely to us, how can you see it? So that's why this is dark ages. Even before CMB, it was a plasma and dark. So that is your first cosmic movie theater started, when you can see the screen. Okay? So how many of you are a little bit confused now? Raise your hand like that. It's very important. Jahang is confused. Shruti is confused. Anybody else confused? Arpita is confused. Very nice. That was the purpose, because I have been confused for 5 months on this horizon, on this inflation, in the beginning dark energy. If you are not confused today, that means you didn't understand anything. Okay? Clear? So now read. My lecture will not give you all the answer. Read the horizon problem, look at the movie. There has been a lot of YouTube videos. And next class you ask me questions and I'll answer you. Okay?
Okay, sir.
Okay. But if you are really confused about what, you can, I give you 2 minutes to ask me questions if you want to ask your confusion. Let me see. It doesn't mean I'll answer you. You have to read, but let's see. You have any questions? Or you want to remain confused till next class? Is that okay, no? And read it out.
Sir, if the universe was like 0.3 million years old, then the edge of the observable universe will be like 0.3 million light years, right?
From where?
If we assume a central point of expansion, then
That time, if there was an observer there, for them there will be a 0.3 million years.
Right.
Not from us.
no, from their point of view.
There is an observer inside them.
So then you said that like the dimension of the bubble is also like 0.3 million light years.
Not dimension, the causal size.
That means a person inside, if a person existed inside that bubble,
Here.
he'll see like 0.3 million light years apart.
And for me now, you can replace persons by photons.
Okay, fine. Okay, for photons. So
can continue traveling within that, because they have traveled this much distance. So this photon of this diameter end will be in causal contact with this photon, because they have been able to communicate. But this photon here will never get time to communicate with this photon. Unless before that there was some crazy thing happened. Maybe they were all together and blown up to infinity.
my doubt is that if the then existed universe was like 0.3 million light year in dimension, so everything should be like, if you said that this a photon inside will see what is there within 0.3 million light years.
Huh.
So everything was inside it right then.
Universe is much bigger, but they will see this much.
Okay.
The size of the horizon is how much you can observe, how much you can equilibrate, how much you can communicate. But the actual universe is much bigger. And that is the reason things can enter horizon and things can leave horizon. How come stars can enter your horizon if there is nothing outside?
Yeah, that's a point.
Okay? Yes.
Okay. Yeah, okay, sir.
So think about it. These are one of the toughest concept of physics. But mathematics is arithmetic. Okay? I'm just doing arithmetic. But the concept.
Sir,
Yes? Yeah?
related to like now Jahang's question, like all these bubbles of like 0.3 million light year size is drawn like with related to the today's universe, right? Is they are expanded to different parts. I mean, all parts equally. So if we go back in time,
I got your point. They are expanded now. But what light is carrying information is not what has happened as per expansion. The light you are seeing today is that time only. Because you are seeing a snapshot of the baby universe. So even if they have expanded after much bigger, that doesn't matter. The light we are seeing 2.7 Kelvin is the time, that time only.
yes, sir.
Yeah. So go ahead. If you have, what is the question?
So like if we go back in time, these has to be together, right? Like how can we say that
Has to be?
all these bubble patches has to be together, right?
No, it might not be. That is the problem, because if suppose this bubble has a temperature 500 Kelvin, this bubble has a temperature 2 Kelvin, this bubble has a temperature 7 Kelvin, different causal connections like different balls, and which are closer they will have similar temperature, but outside they have a complete different distribution of CMB temperature, not at a uniform 2.7 Kelvin. Then they might not be together. Why they have to be together? See, in the beginning, if there was not a super expansion of exponential, the space does not move much faster than the speed of light. You can never cross a distance this much. Can this bubble and this bubble cannot travel this much? There was not enough time, because between this bubble A and this bubble B, this distance, if the bubble has to travel by at least by less than the speed of light, it needs way more time than the time of CMB. It needs billion years. But universe has only existed million years. So how come this bubble and this bubble can travel this distance? That means they have never been touched. To travel, you need some time, no?
Yes, sir.
And there was not enough time simply. And you cannot travel, anything cannot travel more faster than speed of light. So how come this bubble and this bubble can be separated? Because the distance between them is way bigger than the horizon size, and horizon size is nothing but how much distance light can maximum travel from the beginning of universe till the time of CMB. So this is this diameter. So how can you cover this empty space? Huge distance. It is almost like saying that you all move in the platform, say the track is taking you, and you are moving in a velocity of 5 kilometers per second, and I give you 10 minutes or 1 hour. Then you should be at a distance 5 kilometers more or less away from each other. But suddenly I see that one of you are in 100 light year away. Then the problem comes, how come he moves so fast away? Because you don't get time and you cannot have more velocity than light. Then only option is the empty space has supported you. In special relativity, the particles or things cannot move faster than the speed of light. But empty space can move faster than the speed of light. That is not ruled out, or that is not prohibited by special relativity. That's why exponent AT goes as e to the power 100 times t. That lambda is 100. Then within microsecond you will go to infinity. Or if the lambda is say 1 million, exponential blow up will happen. So even if you are together a tiny patch of universe, that will one will go here, another will go here, another will go here, and you look at them and you say that how come they come so far? Because they have not traveled by themselves. The space has taken them. And that's the only solution, and that is called the inflation before the Big Bang. Like a dark energy domination number 1. Because only in dark energy you can have an exponential expansion. Other time t to the power 2/3, t to the power half, we know that it will not going to help you. They are all more or less like velocity of light. Clear? Yes?
Yes, sir.
Getting little clear? Yes? Yes. Ask these questions and it will be clear next time. Okay? Read it. Try to get it in your bone. Try to get it in your blood. Then only you can feel about this universe. Okay? Good? Okay. Very nice. See you next class. Okay?
Thank you, sir.
These things you have to read. Horizon problem, physical length scale, okay, horizon crossing we have done today, horizon crossing. Come inside horizon and in dark energy they will leave the horizon. So in between for some time you see the beautiful universe. Okay, all these things. Okay, great.